Welcome to STEM Cafe. Welcome to the class. Welcome back to the class. If you are just joining us, this STEM Cafe where we make everything science, technology, engineering, and mathematics easy to comprehend, assimilate, fun, and entertaining. We make everything STEM very interesting. Now, we have been acquainted with some tools which we can refer to as standard results. We have done that of x raised to the power n, we have done that of x raised to the power n. We have talked about some rules, product rule, quotient rule, and shade rule. We have also done that of sine and some other trigonometric ratios. Now let's increase our tools so that our work will be easier later on. We have said it is to make our work fun. We are going to talk about our special exponential, e raised to the power x. The number e is a very important number in STEM, especially in physics and chemistry, even in biology, where we are talking about decay, growth, radioactivity and co. Later on we get into that. So this e raised to the power x, so that we don't get diverted or distracted, we can represent it with this summation. X raised to the power 0 over 0 factorial. So, sorry, it begins from 0 plus x raised to the power 1 over 1 factorial plus x raised to the power 2 over 2 factorial plus x raised to the power 3 over 3 factorial plus x raised to the power 4 over 4 factorial. Like that, to infinity. And I believe we all know what factorial is. Like 3 factorial is equal to 3 times 2 times 1. Like that. 0 factorial is equal to 1. And 1 factorial is equal to 1. So since we have known this, we don't need to delay our work again. Now, I have been able to tell you this is e raised to the power x. And normally, in those instead, we always want to make things easy for ourselves. Though outsiders, we see that, oh, these people are making things hard. No. Now, once you have it like this, let us try to differentiate. Okay, let me write it out as it will be. So e raised to the power x raised to the power 0 is 1. 0 factorial is 1, so this is standard 1. X raised to the power 1 is 1. 1 factorial is 1, so plus x. Get that? So we continue like this, x squared over 2 factorial plus x cubed over 3 factorial plus x raised to the power 4 over 4 factorial plus like that. Now, let me now differentiate this. And in calculus, we can have y to be equal to function of x. So if I want, I can just say d dx y. So it's going to differentiate y with respect to x. Please take note, because that's what I'm going to do here. Differentiate y with respect to x. Now, I can now write this as d dx e raised to the power x. You can see, if I differentiate this one, it's going to give me 0. If I differentiate this one, it's going to give me 1. The next one is going to give me 2x over 2 factorial. If I differentiate this one, it's going to give me 3x squared over 3 factorial. The next one, 4x cubed over 4 factorial, plus like that. At the end of the day, it's going to give me 1 plus 2x over 2 times 1 plus 3x squared over 3 times 2 times 1 plus 4x cubed over 4 times 3 times 2 times 1. So this one cancels like this. So at the end of the day, I'm going to have 1 plus x squared. I pointed it out. 2 times 1 is 2 factorial. So, x cubed over 3 factorial. So by the time you compare this and this, you can see everything is the same. So for this special number, d dx e raised to the power x is equal to e raised to the power x. So please, this is another standard result that you have gotten. Add it to the ones you have before. So this special number e, has made it possible for us to differentiate logarithm. But special situation. Let me put it that way. When we have y equals to e raised to power x, the y dx is still e raised to power x. We have established that. Now, if we now have y equals to ln x, please take note. When we have a number like this, ln x, it means log x to the base of e. That is what ln x is. You know, normally if you have a number, if you have a situation where we have log a, most times it implies that this is log a to the base 10. When we have ln x, it means log x to the base e. Is that clear now? So please take note of this. Take note of this very well. It's very, very key in this subject, in mathematics. Now, because I have ln e, I can also do something like this. X will be equal to, okay, so I can now write for e, let's continue, y equals to log ex. So it's the same thing I'm writing now. So I can now write that x equals to e raised to power y. You can see. Now, because I have this situation, I can now try to say, okay, let me differentiate both sides with respect to y. Differentiate with respect to y. So you know what that will be? It's going to give me dx dy is equal to e raised to power y. See, it's very funny. Dx dy is now equal to e raised to power y. You know where we started from here. Now, what will be dy dx? Dy dx is equal to reciprocal of dx dy. Therefore, dy dx will be equal to 1 over e raised to power y. 1 over e raised to power y. And look at this. If you look at all what we have written here, x is equal to e raised to power y from this. X equals to e raised to power y. You can easily decipher that. And that will be 1 over x. That's another standard result established. So we can now say that d dx in x is equal to 1 over x. You can see, I deliberately, made it in this sequence. We have established two results instantly now. That is, d dx e raised to power x is equal to e raised to x. And d dx in x is equal to 1 over x. Very simple. There might be other ways of getting the standard result, but I have told you I make everything easy. Just as I have talked about products, quotients, chain, we can also talk about implicit function. Implicit function is a situation where we cannot easily make y the subject of the formula. Look at this. If I try to make y the subject of the formula, I will model things up, and even if I succeed at the end of the day, to differentiate will be very difficult. But when you have it like this, you can still differentiate easily without going through the rigor of trying to make y the subject of the formula. And what do we apply most? We apply the product rule most times. Product rule. Sometimes you can have it like this, y squared. You can have xy even in the question, in the expression. Let me even see if I can get one. So look at this now. It contains xy. So if you try to make y the subject of the formula, you just, and even at the end of the day, after you succeeded, you'll be having an expression that you might never be able to differentiate. So what do? We refer to this expression as implicit function. But the ones that you can easily make y the subject of the formula and then differentiate easily, those ones are referred to as explicit function. So since we have this situation now, we apply product rule, and it makes the job very easy. Now let's quickly look at this. X squared is x times x. This one is 2 times x times y. This one is 3 times y times y. And we have already discussed that once you have function like this, you can get the total differential by differentiating each part and later on summing it. Now if you look at this, you can say, okay, dy dx of x squared is equal to 2x. Look at this. Because you have known this, is x raised to power 2. But look at this. It is the product of x and y. So 2 is constant. Let's put it there. Now, for me to differentiate x and y now, what am I going to do? I'm going to have x. If you differentiate this one, it's going to give you dy dx. You can see. Plus y. If you differentiate x now, it's going to give you 1. You did that. You can see. It's the sum of the, let me see. It is the differentiation of this, applying the product rule. Now look at this now. 3. If I should say, okay, differentiate this now, I'm going to have, it's y squared. I'm going to have into y squared, into 2y dy dx. You understand? It's going to be like y dy dx plus this one. It's going to be y dy dx plus the second y. Now, dy dx. You can see. What is this one? 0. You can see now. So, this is how you look at it. You look at it like, oh, I'm having product of this. So at the end of the day, you will just make the y dx the subject of the formula. And your answer will now be in terms of x and y at the end of the day. Your answer is going to be in terms of x and y at the end of the day. So look at this again. But for me, I don't know if somebody taught me this, or maybe I just discovered it for myself. What I do most times is this. Like this one, x squared, once you have gotten into integration, the reversal of this, or differential equation, you can write this one, x squared, can be referred to as, this one, you can have 2x dx. When you have x, dx squared is equal to this. Do you understand? Because if you have dx squared dx, it's going to give you 2x. So you can say dx squared is equal to 2x dx. You see? Now, I just want to give you a hint. If you are confused, don't put this one in your test or exam. It's just for your practice. Over time, you will get used to it and you'll be able to write it down like this, straight. Let me just tell you what I do. So for this kind of expression, it's x squared plus 2xy plus 3y squared equals 4. What I do most times is this. This one is x squared. I just write 2x dx. You can see. Plus, this one is going to give me 2x dy plus 2y dx. You can see. Plus 3 times 2y dy is equal to 0. After I have done this, I will now divide through by dx. Divide through by dx. Please, I have said it. This is for me. I can't remember, maybe a teacher taught me, or I just got it by myself. Maybe it's in differential equation, maybe. So what do I do next? I just divide through by dx. So this will be 2x plus 2x dy dx plus 2y plus 6y dy dx equals 0. So if you look at this one and this one, you can see it's the same thing. So this one makes it easy for me. Until after I've gotten proficient with this, I can easily do it like this. So this is the essence of using implicit function technique. So I don't need to start saying, oh, what is y, before I now start going to do the differentiation. That is it. So if you solve for dy dx here, and you solve for dy dx here, it's going to be the same thing. So let's do this. So I'm going to have dy dx into 2x plus 6y is equal to minus 2y minus 2x. So dy dx will be equal to minus 2 into y plus x over 2 into 3y plus x. So it's minus x plus y over x plus 3y. So you can see. So implicit functions makes the job very easy. Don't let me waste time on this. Just get it. Later on when we are practicing questions, we'll get it further. Now with this, that we have understood implicit functions, we have been able to get the logarithm, the differential of logarithm and e raised to power x. Let's quickly look out for solving y equals to e raised to power x and y equals to log ax. Now, let's start with this. Y equals e raised to power x. I can now say that ln y is equal to x ln a. You can see x ln a. And we have been able to, we have known that dy for ln x, dy dx is equal to 1 over x. So, dy is dx over x. That is the differentiation of this over the number itself. That's what it is. We will now apply this here. So, this differentiates both sides now with respect. So, it's going to give me dy over y. You remember, is equal to dx in a. Is equal to dx in a. Now, like we did before, let's divide both sides by dx. So we are going to have dy dx is equal to y in a. And from the beginning, our y is equal to a raised to power x. Therefore, dy dx is equal to a raised to power x in a. So, if we are differentiating a raised to power x, we are going to have a raised to power x in a, or a raised to power x log e. That is the answer. So please add this one to the standard results. You might not need all this depending on your level. But if you are doing A level or you are in the entry level in our higher institution, you will need all this. Now let's work on y equals log ax. Y equals to log ax. Now, from logarithm, we know about change of base. We know about change of base. And that's going to be y will be equal to log ex over log e. Remember about change of base of logarithm. Y is equal to log x to the base of e and log a to the base of a. Remember. Now, we can now say y will be equal to log ln x. Sorry, let me put it that way. Ln x over ln a, which is equal to ln x times 1 over a. You can see this stands as constant now. Ln a stands as constant. Now, and we have done this before, that is d dx y equals sorry. We have done this one before. D dx in x equals 1 over x. We have done this one before. Therefore, we can now say established for when y equals to a raised to the power x, the y dx is equal to a raised to the power x in a. When y equals to log ax, the y dx is equal to 1 over x in a. So we can add this one to our results now. Now for a situation like this, when y equals to e raised to the power kx, and we want to work it out, we are going to add something like this. Y is equal to e raised to the power u. And from our knowledge of chain rule, we can now say dy dx is equal to this one, e raised to the power u dot du dx. Remember chain rule. So it depends. If k is any constant, we are going to have this one to be k raised to the power kx. It might not be constant sometimes. So I mean an expression. So you have to do it like this. Okay, let me do it like this. Y equals to e raised to the power fx. So the y dx is equal to e raised to the power fx d dx. So this, you can see it's not hard. Just know this one by heart, please. Now let's look at another one. Then we have y equals to in fx. You know, we are going to have something like this. The y dx at the end of the day is going to give us the differentiation of this over fx. You get it? Just let me asterisk this. Don't worry, but just keep it in your journal. I also like us to look for cosec sec and then cot. Let's see how we can get this one. Let's start with this. 1 over sin x. So if I want to differentiate this one, what do you think I should use? Let's use quotient rule. Let's use quotient rule. And what would that be? So d dx is equal to sin x. What is differentiation of 1? 0. Minus 1 cos x divided by sin square x minus cos x over sin square x. So going to sec x, 1 over cos x. So if I'm going to differentiate this, 1 over cos x. So it's going to give me cos x into, what's differentiation of 1? 0. So it's constant. Minus 1. What's differential of cos x? Minus sin x over cos square x. So which is going to give me sin x over cos square x. So I can now express this one as tan x over cos x, which is tan x sec x. Depending on how you want it, you might say sin x sec square x, whatever. So this is the result for this one. So you can keep this one too, or just have the idea of how to derive it. So it will make your work very easy. You can see that derivation is very easy. Now let's go to that of tan. Now, if we have y equals 1 over tan x or cos x, how do we arrive at the differential? We are going to have it like this. Tan x into what? 0 minus 1 into what is the differential of tan x? Sec square x divided by tan square x is going to be sec square x over tan square x minus. So, what do we have now? We can now say minus 1 over cos square x tan square x, which is minus 1 over sin square x, which is minus cosec square x. So you can see the derivation of all of these are very simple. What did we apply here? We applied the quotient rule. In the other one, for the implicit function, we applied the product rule. So